In this video, I'm going to talk about line integrals. Alright, so what is a line integral and what are we really looking for? Well, let's look at a curve, which we're really talking about a curve when we talk about a line integral. So we talk about a curve C. And a line integral of f, so f of two variables, x, y, along C, is this. So what we're going to do is we're going to assume that C itself is smooth. It's a smooth curve. Well, what that provides you is that you know that C itself is continuous and its derivative is not 0. Okay? When we talk about a line integral of C along, or f along C, what we can imagine is, let's imagine F's domain, C being in F's domain. So we'll just say, like, for example, F's domain is something like this, right? The domain of F, a multivariable function. And so what we're doing, we're integrating along that curve. So we're just taking the, let's draw a three-dimensional graph. How about that? We'll say x here, we got z, and we have our y. So we have some sort of multivariable function, f of x, y, and in its domain we have c, some sort of curve. Okay, so c is this two-dimensional parameterized function that's smooth. And when we talk about the line integral, what we're really doing here, guys, is we're finding this curtain, this area of this one side of this curtain between F and C. Right? So that's all we're really doing, is finding that area. All right, so the question is, how do we do that? Well, looking at C, we can look at these small changes in C. So we would say change in the distance S, right? So S for distance here. Change in distance S, which if it's small enough, right, we're talking about ds. And we also want the value here of f, right? The value of f. So if we multiply the value of f, right, at some point above C, and multiply that by the change in C, it's similar to single variable calculus, right? And we integrate that, we sum up that multiplication throughout that curtain, we're able to get the area. So we know that the length of C, right? We know that the length of C is L. Let's say L. Okay. The integral of a to b of the square root of dx dt squared plus dy dt squared All right? And again, that was in 10.2. We went over that in 10.2, so I won't go over that again. So this is your length. And we know that our height is f. So what we do is we think of these two ideas, and the line integral of f along c is the integral from a to b f of x, y. Now, we have to parameterize this curve. So this is going to be x of t. All right, so you use substitution. Y of t. So there's your f value, your height. And you're multiplying by the length, the minuscule length of c. And this is how you calculate the line integral. So what I'm going to do now, so again, if we're looking at this equation for the line integral, here we have f, your x and y are in terms of t, and your length of your curve. And you're multiplying the two, you're getting area. And you sum up that. All right, so what I'm going to do now is just do the example. So I'm going to go to example 1. All right, example 1 on page 1076. So this is a pretty simplistic example here. We're talking about a curve. Semicircle. Okay. We have x squared plus y squared. We have the unit circle here, actually. So C is this upper half of that unit circle. And the book is asking us, okay, well, let's find the line integral (2 plus x squared y ds. The first issue here is that we're going to have to parameterize the function x squared plus y squared equals 1. So that's the first thing we've got to do. We know that, well, we're talking about unit circles, so this is pretty simplistic here. We know that x is going to be our cosine t, and our y is going to be sine t. Now, we're not going full circle, so our parameter t is going to go from 0 to pi. All right. So now, basically, we just plug into that formula 3 that we had just talked about here. Let's write the integral down again. Let's follow what the book's got here. That's going to equal 0 to pi. 2 plus, now our x is cosine t, so we just go ahead and we plug that in, cosine t squared. And our y is sine t, so it's just sine t. Okay, we're talking about here in this terms, it's kind of like the length of c. So dx dt. So dx dt, so we take the derivative of x with respect to t, so cosine t, that's sine t, so it's sine t squared, plus, now we got to do dy dt squared. Dy dt is going to be dy ytt squared, or its cosine squared. And then that's dt. Now you're just going to go ahead and do the integral, and you'll end up with 2 pi plus 2/3. All right, so you can go ahead and read section 16.2. I just want to make a quick note that, and I think this for some reason gets confusing for students, is that here I'm talking about a line integral that refers to an area of that curtain or sheet or fence, or however you want to talk about it. But in the second part of 16.2, the book goes into actually finding the line integrals of vector fields, right? So that's different, right? So that's different. When we talk about line integrals of vector fields, we've got this line integral. Well, we got this line, or this curve, right? This curve. And your vector field, we're talking about the work that's being applied on this curve, all right? And the way that's calculated is different. So you want to be able to distinguish between, if I'm asking you about line integrals and a line integral of a vector field, keep that in mind. And that formula, that information starts on page, so this is the line integral of a vector field. That's on page 1083, which is different from what I had just mentioned. Prime example is work, right? Work done. An example of a line integral, scalar line integral, is, we talk about maybe density of a wire, right? Linear density of a wire, and you're trying to find the mass of the wire, right? So you end up doing the line integral to find the mass. So this would be mass of a wire when linear density changes. All right, thanks.